topic that we are going to is Laplace transform. In Laplace transform, we will looking at various aspects of Laplace transform, such as the definition of Laplace transform, the region of convergence, properties of region of convergence, properties of Laplace transform, inverse Laplace transform. We will also look at the use of Laplace transform to continuous time LTI systems, such as determining the causality and stability of continuous time LTI system through Laplace transform. We will also be looking at unilateral Laplace transform, which is a special case of Laplace transform. Before we begin Laplace transform, we have to understand the origin of Laplace transform. In order to understand the origin of Laplace transform, we will be looking at a topic called as In order to understand the origin of Laplace transform, we will be looking at a topic called as eigenvalue and eigenfunction. Now, in order to understand the eigenvalue and eigenfunction, we will consider an LTI system whose input is x of t, output is y of t, and impulse response is h of t. For an LTI system, the output y of t can be expressed as convolution of input x of t and impulse response h of t. Since convolution obeys commutative property, I can also express y of t as h of t convolution with x of t. This can be expanded by using the convolution integral, which will be minus infinity to infinity h of tau x of t minus tau d tau. Now let us say that the input applied is e raised to st. If the input applied is e raised to st, then x of t, we are saying input is e raised to st, then x of t minus tau can be written as e raised to s into t minus tau. Therefore, the output y of t can be expressed as integration minus infinity to infinity h of tau. Instead of x of t minus tau, we can write e raised to s t minus tau d tau. Now, if you observe, in the integration, the variable is tau. Since the variable is tau, t is constant. Therefore, e raised to minus st can be taken outside the integral. So, I can write this as e raised to st into integral minus infinity to infinity h of tau e raised to minus s tau d tau. Therefore, the output y of t comes out to be e raised to st multiplied by this integral I am calling is capital H of s, where capital H of s is nothing but integral h of tau e raised to minus s tau d tau. If you observe, the input was e raised to s tau and the output is e raised to s tau multiplied by capital H of s. Thus, the function at the input appears as it is in the output, and this function is multiplied by a constant which is h of s. Therefore, such functions which when applied to the input appear as it is in the output multiplied by a constant, such functions are called as eigenfunctions. Therefore, e raised to st is called as the eigenfunction, and the value by which the eigenfunction is multiplied at the output is called as the eigenvalue. Therefore, capital H of s in this case is called as the eigenvalue. Therefore, since a function e raised to st is multiplied at the output, we get e raised to st at the output. Such functions which when applied to the input appear as it is in the output are called as eigenfunctions. And this function is multiplied by capital H of s at the output. Therefore, capital H of s is called as the eigenvalue. If we focus on the eigenvalue h of s, the eigenvalue h of s can be expressed as integral minus infinity to infinity h of tau e raised to minus s tau d tau. Therefore, function can be anything. Therefore, h can be replaced by x. So, therefore, I can write down capital X of s similarly will be equal to integral minus infinity to infinity x of t e raised to minus s t dt. This is the definition of Laplace transform. Thus, we can say that Laplace transform is nothing but an eigenvalue whose eigenfunction is e to the power st. So, if we observe the definition of Laplace transform, or if we have to define the Laplace transform, we will define the Laplace transform as eigenvalue of eigenfunction e raised to st. This capital X of s can be called as the eigenvalue, and capital X of s is the Laplace transform of x of t. Next, so how do we define the Laplace transform? So the Laplace transform, as we have seen, can be defined as capital X of s is equal to integration minus infinity to infinity x of t e raised to minus st dt. Such a definition of Laplace transform is called as the bilateral or two-sided Laplace transform. Why is this called bilateral or two-sided? Because the limits of integration are going from minus infinity to infinity. If the limits of integration are going only from 0 to infinity, then it will be called as unilateral or one-sided Laplace transform. Here, capital X of s is called as Laplace transform of x of t. Capital X of s is called as the Laplace transform of x of t. Our next task will be to understand the region of convergence. In order to understand the region of convergence, we will solve a couple of examples. Let us say the first example that we will solve is x of t is e raised to minus at into u of t. We would like to find the Laplace transform of this given signal. The Laplace transform is given by integration minus infinity to infinity x of t e raised to minus st dt. But because of presence of unit step in this question, the integration will go only from 0 to infinity. We will substitute x of t as e raised to minus at. Unit step is 1. So e raised to minus at, this is e raised to minus st dt. Therefore, capital X of s can be written as integration 0 to infinity e raised to minus s plus a into t dt. If we solve this integral, capital X of s comes out to be e raised to minus s plus a t divided by minus s plus a within the limit 0 to infinity. Therefore, we get minus s plus a into infinity minus e to the power 0 divided by minus s plus a. Now, for Laplace transform to be finite, we should get here e to the power minus infinity. If we get e to the power plus infinity, Laplace transform will become infinite. But we want finite answer. For finite answer, the exponential term should be e raised to minus infinity. For the exponential term to be e raised to minus infinity, the term s plus a should be positive. Since the term s plus a is positive, we write this capital X of s as e raised to minus infinity minus e raised to 0 upon minus s plus a. Since s plus a is positive, it can be expressed as s plus a greater than 0. Therefore, we can write capital X of s as 0 minus 1 divided by minus s plus a greater than 0. So capital X of s comes out to be 1 upon s plus a, and this can be written as s greater than minus a. This is the Laplace transform of the given question. 1 upon s plus a is the Laplace transform, and the condition s greater than minus a is called as the region of convergence or ROC. This Laplace transform is valid only for the values of s which are greater than minus a. This s greater than minus a can be shown on the graph. Therefore, we will take, this is sigma axis, also called as the real axis. This is j omega axis, also called as the imaginary axis. And such a plane is called as the S plane. Now, on this graph, we have to show s greater than minus a. So, this will be minus a. S greater than minus a is the region to the right hand side of minus a. This Laplace transform 1 upon s plus a is valid for s greater than minus a, and s greater than minus a is shown here by the shaded region. This shaded region is called as region of convergence, and this region is defined as the region for which Laplace transform exists and is finite. Thus, I can say that for the given question, Laplace transform exists and is finite only for s greater than minus a, which is shown by the blue shaded region. Therefore, the blue shaded region is called as region of convergence. In short, it is also called as ROC. We will take another question to understand the region of convergence. This is the second question, for which we want to find the Laplace transform and the region of convergence. We will solve this very similar to the previous question. We will start with the definition of Laplace transform, which is integration minus infinity to infinity x of t e raised to minus st dt. Since the signal present here is u of minus t, and as we know u of minus t goes from minus infinity to 0, the integration here will go from minus infinity to 0. I would replace x of t by minus e raised to minus at. The value of unit step is 1. So this will be multiplied by e raised to minus st dt. The capital X of s can be written as integration minus infinity to 0 e raised to minus s plus a into t dt. I can further write this as capital X of s is equal to integration will be minus s plus a into t divided by minus s plus a within the limit minus infinity to 0. Therefore, I can write down capital X of s as minus e raised to 0, upper limit is 0, minus e raised to s plus a into infinity divided by minus s plus a. Again, for Laplace transform to be finite, we want e to the power minus infinity. If we get e to the power plus infinity, then Laplace transform will be infinity. We don't want Laplace transform to be infinity. We want Laplace transform to be finite. For Laplace transform to be finite, we should get e to the power minus infinity. To get e to the power minus infinity, the term s plus a should be negative. Therefore, I can write capital X of s as minus of e to the power 0 minus e to the power minus infinity divided by minus s plus a. But this is valid only if the term s plus a is negative. For the term s plus a to be negative, we write it as s plus a less than 0. Therefore, the final answer will be capital X of s is equal to 1 upon s plus a, S is less than minus A. As you can observe, the Laplace transform is again 1 upon S plus A. But this Laplace transform is valid only if the values of S are less than minus A. The values of S less than minus A can be shown on the S plane. This is sigma, this is j omega, and this is minus A. So S less than minus A is region to the left hand side of minus A. This Laplace transform exists and is finite only for values of S which are less than minus A. The values of S less than minus A are shown in the graph by the shaded region. This shaded region is called as the region of convergence or the ROC. Thus, how do we define the region of convergence or ROC? The region of convergence or ROC represents those values of S for which Laplace transform exists and is finite. I hope you have understood how to calculate Laplace transform and the ROC. Next, we would understand the properties of ROC. Let us understand the first property of ROC. The first property of ROC can be understood by looking at the signal that we have solved. The signal that we have solved is e raised to minus at u of t, and the Laplace transform for this question was 1 upon s plus a. S is greater than minus a, where 1 upon s plus a is the Laplace transform and s greater than minus a is the ROC. Now, if you observe the signal clearly, the signal contains the unit step function u of t. The function u of t starts from 0 and goes to infinity. Since u of t starts from 0 and goes to infinity, such a signal can be called as a right-sided signal, which I have abbreviated here as RSS. So RSS stands for right-sided signal. So whenever the signal is right-sided, ROC is always S greater than minus A. Greater than minus A because minus A is the pole of the system. So if I have to generalize, then I will say if x of t is right-sided signal, if x of t is RSS is right-sided signal, then ROC is S greater than sigma max. So ROC will always have the greater than sign, and here sigma max is the maximum real part of poles of capital X of S. Therefore, whenever the signal is right-sided, ROC will be S greater than sigma max, where sigma max is the maximum real part of any of the pole of X of S. Let us look at the second property of ROC. The second property can be understood with the help of another question that we have solved. We have solved a question minus e raised to minus at u of minus t. The Laplace transform is 1 upon s plus a, and the ROC was s less than minus a. Now, if you observe, this signal is multiplied by u of minus t. U of minus t starts from 0 and goes to minus infinity. Since the signal starts from 0 and goes to minus infinity, such a signal is called as left-sided signal, which I have abbreviated here as LSS. For a left-sided signal, ROC will always contain the less than sign, and it will be less than the pole of the system. In this case, pole of the system is minus a. Therefore, ROC is S less than minus a. Therefore, if I have to generalize If I have to generalize, I will say if x of t is left-sided signal, then ROC is given by S less than sigma min, where sigma min is the minimum real part of poles of x of S. Therefore, what we can learn from the first two properties is that if the signal is right-sided, ROC should be S greater than, and if the signal is left-sided, ROC will be S less than. In the first case of right-sided signal, ROC should be S greater than the maximum value of pole. In the second case, if the signal is left-sided, then the ROC should be S less than the minimum value of the pole. Third property, we can have a two-sided signal. A two-sided signal is a signal which contains both u of t and u of minus t. If the signal is TSS, TSS is the abbreviation of two-sided signal. If the signal is two-sided, then ROC of x of S is sigma 1 less than S less than sigma 2, where sigma 1 is the pole from right-sided portion of the signal and sigma 2 is the pole from left-sided portion of the signal. Thus, I would repeat that a two-sided signal has both u of t and u of minus t. Since it has both u of t, it is right-sided as well as left-sided. Since it is right-sided as well as left-sided, we can call the signal as two-sided. A two-sided signal, the ROC is given by sigma 1 less than S less than sigma 2, where sigma 1 would come from the right-sided portion and sigma 2 would come from the pole of left-sided portion. Like this, we can find the ROC of two-sided signal. Fourth, what if x of t is a finite duration signal? If x of t is a finite duration signal, then ROC is entire S-plane. If x of t is a finite duration signal, then ROC is entire S-plane. Therefore, I would summarize the four properties of ROC as the first property, which says if signal is right-sided, ROC has to be S greater than the maximum value of pole. Second property states that if the signal is left-sided, ROC has to be S less than the minimum value of pole. Third property states that if a signal is two-sided, two-sided means it is right-sided as well as left-sided. So it contains both u of t and u of minus t. Then the ROC is given by sigma 1 less than S less than sigma 2, where sigma 1 comes from the right-sided portion and sigma 2 comes from the left-sided portion. I hope you have understood these properties. We will take a question to discuss the properties of ROC. Let us discuss a question to understand the properties of ROC. I am taking the first question, where e raised to minus 2t u of t plus e raised to minus 3t u of t. As you can observe, we have u of t present in both the portions. Because u of t is present in both the portions, we can call the signal as a right-sided signal. Since the signal is right-sided, ROC will be S greater than. Before we find the ROC, let us apply the Laplace transform. So the Laplace transform of x of t is capital X of S. I would directly write the Laplace transform of e raised to minus 2t u of t based on what we have solved. We have already solved e raised to minus 80 u of t. for e raised to minus at u of t, Laplace transform is 1 upon s plus a. Therefore, for e raised to minus 2t u of t, Laplace transform is 1 upon s plus 2. Similarly, the Laplace transform for e raised to minus 3t u of t, similar to this, will be 1 upon s plus 3. Now, if you observe, there are two poles here. One pole is at minus 2 and the other pole is at minus 3. But since the signal is right-sided, I will say ROC of capital X of S is S greater than sigma max. Why did I write S greater than sigma max? Because the signal in question is a right-sided signal. Now, what is sigma max? Sigma max is the maximum pole. As you can see, we have two poles. One is minus 2 and one is minus 3. Which pole is maximum? Minus 2 or minus 3? As we know, minus 2 is greater than minus 3. Therefore, the ROC in this case will be S greater than minus 2. The same can be shown on the S plane. This is minus 2 and the ROC will be region to the right of minus 2. I hope in this example you would have understood how to calculate ROC of a right-sided signal. The next question that we are going to solve in order to understand the properties of ROCs is e raised to minus 2t u of minus t plus e raised to minus 3t u of minus t. As you can observe, we have u of minus t. And here also we have u of minus t. Since both the portions have u of minus t, the signal x of t can be called as the left-sided signal. We will apply the Laplace transform. The Laplace transform for this will be capital X of S will be equal to. Now, what is the Laplace transform of e raised to minus 2t u of minus t? We will use the formula e raised to minus at u of minus t. As you can observe, for e raised to minus at u of minus t, it is 1 upon s plus a. But we have to adjust the minus sign to the right hand side because there is no minus sign here. So, for e raised to minus 2t u of minus t, the Laplace transform will be minus 1 upon s plus 2. Similarly, for e raised to minus 3t u of minus t, it will be minus 1 upon s plus 3. But we are interested in finding the region of convergence or ROC. So, what will be the ROC? Because of presence of u of minus t, this signal is left-sided signal. Therefore, the ROC of capital X of S is given by S less than sigma min, where sigma min is the minimum value of the pole of X of S. Now, we have two poles. One pole is at minus 2 and the other pole is at minus 3. Which pole is minimum? Minus 2 or minus 3? As we all know, minus 3 is less than minus 2. Therefore, the ROC will be S less than minus 3. The S less than minus 3 ROC can be shown on the S plane. So, this point will be minus 3 and S less than minus 3 means the region to the left hand side. The region to the left hand side of minus 3. We will proceed to the next question. In the next question, we have e raised to minus 2t u of minus t and e raised to minus 3t u of t. As you can observe, because of u of minus t, this portion is left-sided portion, whereas because of u of t, this portion is right-sided portion. As the signal has both left-sided as well as the right-sided portion, we will say that the signal x of t is a two-sided signal. What will be the Laplace transform? If I apply Laplace transform, the Laplace transform for this will be, now as we have seen, e raised to minus 2t u of minus t is 1 upon s plus 2, whereas e raised to minus 3t u of t will be given as 1 upon s plus 3. Right? Since x of t is a two-sided signal, according to properties of ROC, ROC of capital X of S will be sigma 1 less than S less than sigma 2, where sigma 1 should come from the right-sided portion and sigma 2 should come from the left-sided portion. So, which pole is coming from the right-sided portion? the pole that is coming from the right sided portion is minus 3. Whereas the pole that is coming from the left sided portion is minus 2. Therefore, the ROC will be minus 3 less than S less than minus 2. The minus 3 less than S less than minus 2 ROC can be shown on the graph. This is sigma j omega. We take two values, minus 2 and minus 3. And the ROC is the region that is between minus 2 and minus 3. This is shown by the shaded region here. The shaded region as shown in the graph is the region of convergence for the given question. We will also take another question in order to understand the region of convergence. The next question that we are solving to understand the ROCs is e raised to minus 2t u of t plus e raised to minus 3t u of minus t. As you can see, because of presence of u of t, this portion is right sided, whereas because of presence of u of minus t, this portion is left sided. Because of the presence of both right sided or left sided portion, this signal can be called as the two sided signal. Right? For a two sided signal, what is the Laplace transform? So the Laplace transform capital X of S will be 1 upon S plus 2 minus 1 upon S plus 3. Since X of t is a two sided signal, ROC of capital X of S is sigma 1 less than S less than sigma 2, where sigma 1 should come from the right sided portion and sigma 2 should come from the left sided portion. So sigma 1 should come from right sided portion, therefore sigma 1 will be minus 2, whereas sigma 2 should come from left sided portion, therefore sigma 2 will be minus 3. Therefore, if you observe, the ROC is minus 2 less than S less than minus 3. You cannot have a value of S which is greater than minus 2 and less than minus 3 at the same time. Such an ROC is not possible. Since the ROC is not possible, we will say Laplace transform does not exist. I would repeat, why is the ROC not possible? Because you cannot have a value of S which is greater than minus 2 and less than minus 3 at the same time. Since you cannot have such a value of S, we will say that the ROC does not exist. And since the ROC does not exist, we will say the Laplace transform does not exist. Therefore, if such a question is asked, you have to say that the Laplace transform does not exist. The next question for which we want to find the ROC is e raised to minus 2 mod t. So what is mod t? Mod t means it should be replaced by t for t greater than 0, it should be replaced by minus t for t less than 0. Therefore, I can write x of t as e raised to minus 2t for t greater than 0 and e raised to 2t for t less than 0. Therefore, I can write x of t as e raised to minus 2t. Since e raised to minus 2t exists only for t greater than 0, we should multiply it by u of t. Whereas, since e raised to 2t exists only for t less than 0, we should multiply it by e raised to minus t, u of minus t. Now, if we apply Laplace transform, the Laplace transform of this will be e raised to minus 2t u of t will be 1 upon s plus 2, whereas e raised to 2t u of minus t will be minus 1 upon s minus 2. This can be calculated from the formulas we have derived earlier. Now, if you observe the signal x of t, because of presence of u of t, this is right sided, but because of presence of u of minus t, this is left sided. Since we have both right sided and left sided portion of the signal, x of t can be called as a two sided signal. Since x of t is a two sided signal, ROC for capital X of S is sigma 1 less than S less than sigma 2, where sigma 1 should come from the right sided portion. The right sided portion is the first half of the signal. Therefore, sigma 1 in this case will be minus 2, whereas sigma 2 should come from the left sided portion. The pole from the left sided portion is 2. Therefore, sigma 2 is 2. Is this ROC possible? the ROC is possible because you can have a value of s which can be less than 2 but greater than minus 2. Therefore, the ROC here can be shown as the region between minus 2 and plus 2. And since the ROC exists, we can say the Laplace transform exists and is given by this formula 1 upon s plus 2 minus 1 upon s minus 2. If you simplify this in the simplified form, this can be written as minus 4 divided by s square minus 4, which will be the Laplace transform for the given question, and the ROC will be minus 2 less than s less than 2. In the next question, we have to find the Laplace transform and ROC for x of t is equal to delta t. As we all know, delta t is the unit impulse signal. How do we get the Laplace transform? So we will try to find the Laplace transform by using the definition of Laplace transform, which is integration minus infinity to infinity e raised to minus st x of t dt. Therefore, capital X of s will be integration minus infinity to infinity. This will be e raised to minus st into delta t dt. In order to simplify this, we have to use a property of unit impulse. The property of unit impulse is x of t into delta t. X of t into delta t, if you remember, we get x of 0 into delta t. Therefore, e raised to minus st into delta t, we will get e raised to minus s into 0 into delta t. That is, when the function is multiplied by delta, t becomes 0. So, since the function is multiplied by delta, here t becomes 0. So, we get delta t. Therefore, this integral will become capital X of s is integration minus infinity to infinity delta t dt. Now, integration of impulse is area under impulse, and as we have seen by the definition that the area under impulse is always 1. Therefore, capital X of s is equal to 1. Therefore, the Laplace transform for unit impulse signal is 1. Now, the question is, what is the ROC for the unit impulse signal? Before we find out ROC, we have to first categorize whether delta t is right-sided, left-sided or two-sided. If we draw the diagram of delta t, how do we draw delta t? So, delta t is a signal whose amplitude is going to infinity. Delta t is a signal whose amplitude is going to infinity, hence it is shown by arrow. Besides the arrow, we write 1, where 1 indicates the area of the impulse. As you can see that the impulse is neither right-sided, nor left-sided, nor two-sided. An impulse is categorized as a finite duration signal. So, the impulse in the question here is a finite duration signal, and as we have seen from the fourth property of ROC that for finite duration signal, ROC is entire S-plane. ROC is entire S-plane, hence this can be shown as this is sigma and this is j omega. Since the ROC is entire S-plane, we will shade the entire S-plane. This is the ROC for the unit impulse signal. The next signal is u of t. So, we have to find the Laplace transform and ROC for this unit step signal u of t. We will again solve this question by using definition of Laplace transform. The definition of Laplace transform is capital X of s is equal to minus infinity to infinity e raised to minus st x of t dt. Since we have unit step u of t, the integration will go only from 0 to infinity. The value of unit step is 1, so this will be e raised to st into 1 into dt. Therefore, we have capital X of s as integration 0 to infinity e raised to minus st dt. The integration of e raised to minus st is e raised to minus st divided by minus s within the limit 0 to infinity. Therefore, capital X of s can be written as e raised to minus s into infinity minus e raised to 0 upon minus s. Again, for Laplace transform to be finite, the exponential must contain e to the power minus infinity, because if you get e to the power plus infinity, then the Laplace transform would become infinite. We don't want Laplace transform to be infinite. Therefore, we want e to the power minus infinity. If you want e to the power minus infinity, then s should be positive. So I will say s should be positive. Since s should be positive, we will write x of s as e raised to minus infinity divided by e raised to minus 0 into minus s. The condition on s is that s should be positive. Therefore, s should be greater than 0. Therefore, capital X of s comes out to be 1 by s. Therefore, the Laplace transform for unit step signal is 1 by s. And the ROC in this case is s greater than 0. We will draw the s greater than 0 ROC. The s greater than 0 ROC is the region to the right hand side of j omega axis, as j omega axis represents s is equal to 0. This is the ROC for unit step signal. Therefore, the Laplace transform for unit step signal is 1 by s, and the ROC is region to the right hand side of j omega axis, represented by s greater than 0. The Laplace transform of unit step is very important. The Laplace transform of unit step is very important. One must remember the Laplace transform of unit step.